because they can feel.
Yeah.
Like you can feel one node give to the other when you're doing like this.
Distance.
Yeah. I'm doing physics 222.
I took an extra amount of time explaining this to Brian and talking to him with it because waves or something are cross again later.
Yeah.
But other than that, like that, the explaining it and talking to them took like 20, probably like 25 minutes to get started. Then, and then we still ended up losing for seconds early.
Funny coincidence. I was actually talking with one of my students in 223 lab today about the Clebsch-Gordon coefficients.
Why?
Because he was studying organic chemistry,
Yeah.
and I was asking him if he knew like where spin orbitals came from.
Cool.
I'm not sure if that's going to be in chapter 5 or if that's a next semester thing.
Next semester.
Gotcha.
That is addition of
Angular
momentum.
Okay, good.
Thank you.
Alright, so today we are going to start a new topic about the angular momentum. The angular momentum most important is when we deal with from 1D, right? One dimension to either 2D or 3D. So when we go to the higher dimension, we know in addition to the linear motion, we will have a rotation. So then when we deal with this type of system, before we dealing with this, we need to understand what is angular momentum. It's rotation, hyperized rotation, right? So we need first understand this behavior of the angular momentum. Then we go to the higher dimension of motion of the system. Then we're going to not only consider this Hamiltonian and also angular momentum. So that is the basic topic which is called chapter 5. First is a general formalism of the angular momentum. Then the property of angular momentum, then we are going to study or introduce spin angular momentum. Then we go back to familiar with orbital angular momentum, right? So we go back to here and discuss the details of the eigenstates in the position representation. So first, operator, right? The angular momentum operator, if we use L, now, let's start. L is operator, right? So the operator, usually we have in the classical, the operator, variable operator A is correspond to A in classical mechanics, right? Classical or physics, right? Let's say classical physics. So how to convert one of the classical physical quantity from classical physics to quantum mechanics is operator in chapter 2, we already discussed the operator if, just remember, try the R operator, the position operator is correspond to position in the classical physics, right? And the momentum operator is we have the momentum in the classical physics. So the Hamiltonian operator is kinetic energy operator plus potential energy operator. Kinetic energy operator is this, right? So if we know the momentum operator, then we can build up this function of operator. The Hamiltonian is a function of operator momentum and position, because this is usually is a function position. So now today we are going to find the orbital angular momentum, right? This is one of the angular momentum is, so from here, okay, that is the T square plus 3, right? That is, and then the angular momentum. Orbital angular momentum, we know this classical is a cross product of this, right? So immediately we can have this orbital angular momentum is the cross product of a position operator with the momentum operator. So that is the initial way to give us this operator, this angular momentum or orbital angular momentum. So here we start from here. Even though we are going to derive the general formalism of a general angular momentum, but we start from orbital since we're familiar with this one. Then we are going to study the general feature of the orbital angular momentum, then extend to the general. Since if general the angular momentum has a property, one of the special angular momentum, orbital angular momentum we have the same. Right? So we start from the specific case and extend to the general. Okay, so now let's first look at this one. Let's in the position representation, right? Position representation. Since we are going to represent this operator in either position matrix representation, depending on the different type of the representation. So in position representation, we know R is, right? So that is x plus I plus C. And the momentum operator is this one, right? So now let's see in the position, that's Cartesian. So in the Cartesian, then this one is a gradient, which is okay. These three components, right? That is the operator. So the L, the orbital angular momentum, the operator here is the here. Okay, so let me just first write down here, and then that is minus I H bar. Let's use capital R. Cross is gradient, and then that is okay. Either way, so now I think you're familiar with this. So usually I use this one. Yes, matrix to help us. So x, y, z, partial, partial x, partial, partial y, partial, partial z, right? This matrix, so you can get this, the x component for to this one, to project to the I, so that is this matrix, right? So that is y partial z, right? So that is minus I H bar, and the first one is this one multiplied minus this one, so that's y partial z minus 3 partial y, right, along this s, and the second one is y component is this, right, and that is x partial z, and z partial is negative. So that is this one first. Z partial x minus x partial z. That is j components, and the last one is take this. So this is submatrix, right? That is x partial y minus y partial x. Okay. So we have three components, and that makes sense because we know the output angular momentum is vector. Then we are going to introduce Lx, Ly, and Lz. Then by this definition, now we have the expression for each component. Lx is minus I h bar. Y, in principle, you still need to write down here. This is a operator, but since we have, we just keep this as an operator, right? Since we have this position representation in this, the position operator is nice, but it's component. So here, y partial, z minus z partial y, and Ly is minus h bar. Z partial x minus x partial z, and z x partial y minus y partial x. So now we have this operator in this position representation. Okay, so that is the first feature, that is a vector, right? Okay. So that is first, we have a components, and we can write this auto angular momentum in terms of this component. Each operator, components operator is defined here. Now how about this L square? Look, the L square is L model in the product itself, right? So then you can very easily to save that because this is here, right? So this is because Lx, this if this inner product between I and j is perpendicular to 0, so that is very easily you just that is the scalar, right? So that is vector and this scalar, this second property. Then now we are going to prove that this is the first one. So that means it is a vector. And then this is a component here. Then this one, second one, is a scalar. Now, third property is Hermitian because let's do one of these Lx. It's conjugate. So now let's see here. That is here, right? So that is okay. We need to use this one. So this should be like this. Y pz minus zpy, right? This is z multiplied by px minus x pz. And that is x py px. Okay, so that is this one. That is y pz minus z py Hermitian. Then we know if you take the Hermitian, the first term is we take the change in the position, right? Minus p1 Hermitian, z Hermitian. Each one we know they are Hermitian, sorry, the diagram. So they are Hermitian, so p z y minus p y But up to now, these are not equal to the inside, right? Because we have changed position. Can we check? Are they commute each other? Pz, Py commute, right? So I can change the order. Y, Pz, Z, Py. So yes, it is equal to itself. So similar, so Lx is Hermitian. And similarly, the others, Ly is Hermitian, Lz is Hermitian, and L should be Hermitian. So it's the components, and of course, L square is also Hermitian. More easily, right? Or, yes, okay. From here to here, it makes sense, right? Because YPZ, right? They commute. Since this is not the same component, so if they commute, then YPZ equal to PZY. So I can change order. So that is the property 3. That means these are Hermitians. These are Hermitian operators. Okay. That is the property 4, which is be general. If we extend to the arbitrary general angular momentum, so this is number 3 and number 4. What is commutator? Okay. Now since we have components, so we are going to see what is the commutator between the components and between the component with square. So that is very important. Okay. I'm going to direct use. Okay. Because we're familiar with the component, the commutator between position operator and momentum operator. Commutator. Patient relation. This is very important. This characterizes the feature of angular momentum from the others. So now let's look at this one. First, look at this. How about the commutator between Lx and Ly? Are they commute each other or not? So how to do that? We just use what we learned from chapter 2. Lx here, right? So Lx is y pz minus zpy, and Ly is zpx minus xpz. Okay, so now we have 4, right? So this one with this. 4 commutators, right? So now let's go here. Y pz is z px plus, minus because this is a negative here, right? Minus y pz x pz, and then the minus z px py and z px. Then plus z py x pz. 4 commutators, right? Okay, then for each one is also the products. So now let's look at the first one. Y commute with z, right? And y commute with px. Then pz do not commute. We know pz and z has an ion, right? So that is, and then so we have a 4 case, but only this one. So that means we only consider this pair. Then we consider this one. The y is in front, right? Pz, z, and px. From here to here. Any question? If not, I can go further. Okay. Minus. All right. minus this one. This one is clear because y commute with x, y commute with pz, and pz commute with px, pz commute with pz, right? So this term is 0. And number this one is also pz commute with pz, pz commute with px, py commute with pz, and py commute with px. So this one is also 0. The last one here, z commute with x, and z do not commute with, we have a but keep this. So but this one, py commute with px, py commute with pz. So the last one is plus. This is okay, so that x is found, right? X and z, pz, and py. Okay, so now this is this one is z, pz is IH bar. So this opposite, so that is minus IH bar, y, px, right? The first term, because we know the z, pz is IH bar, right? So just opposite, change the order. Then this one is IH bar x py. Now I'm going to take IH bar outside. I don't need to actually. Yeah, IH bar outside. Here, inside. Inside is x py minus y px, right? That is LZ. Is this one. This one. So now we found, yes, the components, the angular momentum, the components does not come together. So now we summarize. Lx, Ly is equal to Lz. Okay, so you can see here, this is like if from, you consider x, y coordinates, so like from x to y, to follow this counterclockwise, then go to z. And similarly, you can do yourself, similarly others, is like this, for example. Ly, you do the same thing and take the result. Lz is IH bar Lx. So y to z go to x, that is counterclockwise, right? Then Lz, Lx is IH bar Ly. If you change the order, just get back it. Okay, that is very important commutator relation. And how to do that, if we know this, right, we just use this, and of course this component, then we can prove commutator relation. That is the categorize of this orthoangular momentum. Now the last one. So this is components. How about the L square? Let's consider L square with Lx, with one of the components. Okay, L square, we know that is Lx square plus Ly square plus Lz square, right? With Lx. Okay, let me. So now Lx with this component. Lx square Lx plus Ly square Ly, right? Sorry, Lx. Z square. So this one is 0 because Lx commute itself. Then this one, let's go to this one. This one is Ly square. I take Ly outside and Ly Lx. And last, another is found one. Alright. And in the same license for Lz. Z, Lx, plus Lz, Lx, Lz. And now we see we have this, right? So we are going to use this relation here. The first one, yx, just the opposite. So they have negative I h bar L y, right? This one, same thing. So negative I h bar L not Ly. Sorry. This one is Lz, right? This one. Minus I h bar Lz. And this one is minus I h bar Lz Ly. Right? Keep in mind the order. This is very important. This one found, and this second, this found, this second. Then this Lz, Lx, is this one is I h bar Ly. So I h bar Lz first, and Ly. And the last one is I h bar Lz, Ly first. And Lz. Then you can see they cancel each other, right? Zero. So this means the square commutes with any component of self. So we have L square y is x, y, z. Any. You do the same thing, right? So you can see from here the commutator of L square commute with any components, or we just write down here. This vector. Since vector is a combination of 2D components, right? So this is an important commutation relation. Now with this, we are going to extend it. These are derived from this auto-angular momentum. Since we know auto-angular momentum how to deal with, start from what we know, the position operator and then momentum operator, linear momentum operator. Now we are going to add operator. So now general, this is now we come to flow. Only this okay. General is to distinguish the orbital angular momentum, we are going to introduce J. So that is general. J may be orbital angular momentum, maybe spin angular momentum, maybe addition of a spin and orbital. So that is general. Let's consider the general orbital. General angular momentum we use J is the vector. So that is definition first. First definition. Introduce J operator. That's the vector. So that is Jx, Jy, and Jz. First, right? So that is a vector operator with this definition. Okay, then properties. Second one. Properties. First, okay, A. J is vector. This is the first time we deal with. Okay, yeah. In one dimension, even though the linear momentum is vector, but the one dimension is still do not deal with other direction, right? So that is vector. So that is the first feature, and then these components here, right? This is Jx, Jy, J. But the detailed expression of this Hermitian, we just say that there is P-Hermitian operator. That is defined. That means we introduce this angular momentum operator. That must be a vector operator. That must be a Hermitian. Since from the orbital angular momentum operator, we already proved that is Hermitian. Then general must also follow this. So that require this must have this. Okay, and then the C, which is the square of this general angular momentum, which is the linear product of 2, which is rho f of j instead of L, jx squared plus jy squared plus z squared. That's number 6. Then the commutation relation follow the same thing. Since if the output angular momentum have the commutator relation between the components, then the general angular momentum we also have same. So D, we will have Jx must be follow this commutator with Jy, I h bar Jz, and Jy, Jz is I h bar Jx, Jz, Jx, Jy. And same thing here, and the J square commute with any component. Okay. Yes, that is the property. All right. So now, next step, when we introduce the general angular momentum, we know it has this property. So next one. We are going to find what is eigenvalues and eigenstate. Eigenstates of J. When I say J, actually include its component, include its square, right? So now. That is the next job, right? How to do that? Remember, right? For any operator, A, if I use A as the notation, this is the eigenstate of operator A, so that A is, that is eigenvalue, right? So this is the eigenvalue, this is the eigenvector, right? So we are going to solve like this. We are going to apply this now. So let's say it this way. J square apply its eigenstates. So be equal to its eigenvalue eigenstates, right? So now here, this notation say that is the eigenstates of A. Now for J square, we are going to introduce another dimensionless numbers. Actually, we call this quantum number, right? To characterize the eigenstates. Even though, so now let me first alpha beta. So that is is an eigenstates of J square. Okay, I think I need that. Okay, let's keep here. So, how to characterize this? Now, let's first look at this commutator. So we know J square commute with any components. However, the component itself does not commute each other, right? So that means J square and Jx, they can form the joint eigenstate, but not states. But the Jx, Jy not, right? So that means because this, so we will find the joint eigenstate is one of the components, or we select Jy or Jz. That means we can not select the general joint eigenstate for J square, Jx, Jy, Jz simultaneously, since these three are not commute each other. So we are going to find the eigenstates that we are going to select one of the pair. J square with Jx or J square with Jy or J square with Jz. And then we are going to find the joint eigenstate. For the remaining two components, we are going to solve once we know this. Right? So we because this, right? So we just select by convenient. I select GS1 and GZ. The United States. Let's look. The United States of G square is GZ. Okay, because either pair has the United States. So with that, then we come to here. Okay, when we select that, then we are going to this one and the GZ is equal to set question, right? Okay. Now we'll introduce the joint eigenstates is all the series of alpha beta, that is the quantum numbers we are going to determine. Quantum numbers characterize the joint eigenstates of G square and GZ. So we need two quantum numbers. One is characterized G square, another characterized GZ. So here, this quantum number, and then that is we introduce. Okay, let's see, introduce. Introduce these two numbers. And these two numbers, we introduce, since the quantum number, usually we just say this dimensionless. Dimensionless quantum numbers. Okay, now we come down to here. So here I'm going, in general, I'm going to say that use some of the numbers, alpha, beta, to, because this character quantum number is not the eigenvalue of G squared corresponds to this number. Eigenvalue GZ corresponds to this number. Now here, instead of writing by one notation, we are going to use H bar square alpha, and here is H bar beta. Okay, so that means we are going to use the eigenvalues of G square. We use H bar square alpha, and eigenvalues of GZ, we introduce this. Instead of A, we use the H bar square alpha, which is give us the eigenvalue of G square. And this cat, alpha beta, is for giving alpha will have the eigenstate correspond to this one. GZ, its eigenvalues be H bar beta. Now the question is, why? Because this is dimensionless, right? So why we introduce H bar? Since this dimensions be form the same dimension, right? So you know that's from this the classical. We just need this classical, because the dimension is same thing, classical quantum mechanics, because it's right. So now you see the dimension of L divided by the dimension this time, right? The derivative equal to here. This one is is energy, right? So that is energy here. Therefore, the L, the dimension for angular momentum speed, energy, dimension of energy multiplied time. And that is really H bar, right? We know H bar is energy. The energy easier you use H bar, we use electron volt, right? And multiply time second. So that's why here we introduce dimensionless quantum number, then to match the dimension of the angular momentum GZ, we have to multiply this. And the G square, of course, is square, right? So that is why we write this way. Write this way, the goal is that we are going to find this quantum number which is dimensionless. Okay, so next job is we are going to find the alpha and beta. Here, since we discussed general angular momentum, no any detailed expression, not like optical angular momentum that R cross product is P. So we have like position representation, we can write the details. Here, this is really general, so we just write in terms of like kind of abstract. Then how to determine these numbers? We are going to use this to help us, right? So now, okay, let's get first, let me summarize what we introduced. So here, this we are going to define as a joint eigenstate, right? Joint eigenstate. And if a joint eigenstate means they are orthogonal, must be, right? We assume that if the joint eigenstate is satisfied like a complete set of this CSU, right? Operating of they are, these two are complete set of the complete operator, right? So, and also SB complete. That is behavior of this joint eigenstates. So we are going to use those properties because we assume they are eigenstates. Then here, there's two, right? So now let's summarize. So and also J squared. TZ. Okay. What do I use? Okay. So now this is the information we know. Now next we are going to find the goal is how to do this. We are going to use the in the harmonic oscillator we apply the algebraic method, right? The algebraic method we introduce raising or lowering or creation or and hidden operators to try to help us to determine the n, right, the quantum number. So we are going to use the same thing. So in order to do this, let's use number 18. Yes, okay. So now this is number 4. We are going to do this, right? First, introduce. We are going to, since follow the algebraic method, introduce J plus minus. And J plus minus, you will see that play like raising or lowering the states by 1 unit. So how to determine this one, like A and A dagger in this case, J plus minus is simply the Jx plus I Jy. That is just simple. When we introduce this, so you will have several properties here. Okay, first, let's see the Hermitian. Let's see. Gx plus I Jy Hermitian, right? And that's Gx Hermitian dagger minus I Jy dagger, right? But Gx, Jy, they are Hermitian. We just proved, right? So then that's Gx minus I Jy, which is J minus. So yes, similarly, J minus dagger is equal to J plus. So J plus minus are not Hermitian. That is important. Non-Hermitian operators. Okay. So that keep in mind. Then when we introduce this, we will immediately have the Jx. Calculate this, you can easily Jx Jy in terms of J plus minus is just half of J plus J minus, and Jy is half of half I J plus minus J minus, right? And then also this you just do square, right? Jx square, I just gave you the result because it's just simply square plus J minus. And be careful, they do not come each other, so the order is not changed. Right? Keep one here. J minus. Square minus 4, because here there's a minus 4, and minus J plus J minus minus J minus J plus and plus J minus square. So this, and then you can see if we add it together, Jx square plus Jy square is equal to this term cancel. This term, only this term are not cancelled because it's acting like a plus, right? So we have a half of quarter plus the half, right? J plus, J plus J minus plus J minus J plus. This is one of the important relations here. And you know this one is equal to J square minus Jz square. So now the relation here, we will use later those kind of relation here. Okay, now this is when we introduce J plus minus, we can have the relation between J plus minus and J square and also J square Jz. Now the commutator. Okay. Commutation, rotator, relation. Between J plus minus and J square and Jz, because we are interested in these two, right? So we are going to see what is the commutator relation between J plus minus J square and Jz. Now let's first look at this. How about this one? I think it should be needed, let me know. Do they commute?
Should
This commute, right? And this is just a plus minus this components. So immediately, okay, you do yourself, I just give you a result. Right? Okay. But we are not interested in the we are interested in if they commute. So J square J plus minus equal to J plus minus J square. We are going to use this relation here. Let me give an equation 1. We're going to use this later. Let me try to obtain this content numbers. So this is the first one. Second one, the commutator relation between J plus J minus. This one, J plus Jx plus Ijy, and J minus Jx minus Ijy, right? So we are going to use the commutator relation between Jx, Jy. This one commute, right? Only this not commute, and this one not commute, this one not commute. So we have 4. Then the result is, okay, the result is 2h bar Jz. This is equation 2. So what that means here, okay, just keep it. The number 3 is Jz, the commutator relation between Jz and J plus minus. Okay, so that is Jz with J plus minus Jx plus minus Ijy, right? So we have commutator relation between Jz and Jx and Jz, Jy. They are not commute, right? So the final result, let me give you, plus minus h bar J plus minus. That's equation 3. So this one is, we are interested in this from here, because this is Jz multiplied J plus minus minus J plus minus multiplied Jz equal to this one. So we have a J plus minus equal to, move this term, second term to the right hand side, right? This J plus minus Jz plus minus H bar Jz. Okay. This relation is very important to help us to determine the quantum numbers. Because we need the wreath on the Maury, right? We need the wreath on Maury to apply this eigenstates. Then we are going to find or analyze a lot of quantum numbers. All right, so let's see, that's there are more information we have. Is let's look here. This product, right? This product is Jx I Jy multiplied Jx minus Ijy. and that equal to, you can check yourself, J square minus JZ square plus alpha TZ. And alternately, J minus multiplied J plus is Jx minus I to y, and Jx plus I to y. That is equal to J square minus Jz square plus minus alpha Jz. So these two combined together, okay, J plus minus multiply J minus plus J minus multiply J plus. So that's two add together, you will see a factor 2 J square, right? So there's 2 J square and Jz square. So these two are cancelled, right? So from here, from this one, let's look at this one. So first look to, okay, let me write down here this one. So here, J, this one. See here, J plus J minus plus J minus J plus is half of Jx squared minus Jy squared is equal to this. So here, this one is equal to this one, right? So that is here is twice of Jx squared plus Jy squared, right? J squared minus J, so and then that is this one. Is this one. So that is J plus J minus plus J minus J plus. Okay. Yeah, that's the only reason. So here I just move. Therefore, J square is half of J plus J minus minus plus J minus J plus, and move this to the left hand side, to move this one to this one, so we have plus Jz squared. From the equations, so we have 4, 5, then we have this one is 6, so this one 7. Then from 4 and 5 they combine together, we got this one. If this combine together here, this J square, move this to the left hand term, right? So J square equal to J, if this one, so that's plus minus, right? So that is J, J plus J minus, and J plus J Z square and minus H bar Jz, right? That is from before. But now 5 all are same. Only the difference here, right? So that is I'm going to use. That is 8. Okay, we use this. Okay, I think that's enough. Now let's declare for number. Okay, so keep again. So now we are going to apply G plus minus on the eigenstate. Now we are looking for what happened if this operator apply this. So now let's look this one. Let's look at Jz and G plus minus apply this. Let's look at this. It here, right? Jz, J plus minus equal to J plus minus Jz plus minus H bar Jz, right? So because this one equal to J plus minus Jz, that is use this equation. I didn't give a number of this equation. Right? Okay, this number actually is 3. since this comes here, or you use reply. Plus minus h bar jz alpha b. Because we need to find this applied to this eigenstate. Then let's look this the product. The product look this, and then now that's equal to g plus minus jz apply this over here, right? Jz applies h bar beta, right? So we have h bar here. That is this one, and this plus minus h bar square. Okay, because this one is jz plus minus one plus minus h bar jz. No, not this one. Okay, let's do this one. G plus minus and jz is h bar beta. Alpha beta is first term. Second plus minus h bar. Okay. I think I made this.
G to G prime.
Yeah, I think here this is
Plus minus.
plus minus, no? Yeah, that's how it says. Plus minus. Okay, so now we have to take g plus minus. First term is h bar beta. Second term plus h bar, right? Alpha beta plus minus h bar. G plus minus alpha beta. So here that is h bar beta plus minus 1, g plus minus alpha beta. So what that means? Here, if you consider this is a new state, that g plus minus apply this state, the eigenstate of joint eigenstate of g squared gz, then what happened? That's this new state, when the jz apply this new state, it gives us, this is a eigenstate, eigenvalues, the same states, right? So, yeah, so, what does means? So, g plus minus apply this one is the eigenstate, okay, of jz is the eigenvalue of h bar beta plus minus 1. So that means there has to be, okay, that means g plus minus beta is equal to sum of coefficient. I'm going to use alpha beta plus minus 1, right? Since this state is correspond to the eigenvalue of this. The eigenstate corresponds to eigenvalue beta plus minus 1 to be this state, right? Okay, so that means this state equal to this, but with a coefficient here. So we are going to determine the coefficient. This is the first part, right? First, so we have, now second, we also look this one. G squared, G plus minus, apply the state. Okay, so G squared, that is this one here, because it commute. So that equal to G plus minus G squared, alpha beta. And I just erase, but you know that G plus G squared, that is beta, H bar square alpha beta, right? So that means that is H bar square alpha, G plus minus alpha beta. This is alpha. So what that means, the G plus minus apply the states, this states is the same states with the same eigenvalue of the J square. So J is the eigenstate of J square. This eigenvalue of H bar square alpha. So what does mean? So that means J plus minus will alpha beta will change the state to alpha beta plus minus 1, but not change, right? Not change alpha, only change beta. So that means if the J plus, that is makes sense because J plus minus commute is J squared, right? So it will not change this state. So we have, that is first conclusion by analyze these two. Okay. Now we are going to have this relation, so we know that is the row plate. So now let's look this one. We're going to determine something. We are going to determine alpha beta, right? So now let's look this one. J square, we are going to look this plus J y square. Look this guy. It is equal to J square times J z square. So we always larger than 0, right? Because J x squared plus y squared always positive. So what happened? Then assume. Okay. So we have this inner product J square minus J square on this eigenstate thus be always larger than 0 or larger or equal to 0, and that these are eigenstates, joint eigenstates of these two, right? So that means this is h bar square alpha minus h bar square beta square alpha beta. So that is h bar square alpha minus beta square alpha beta. Thus we always larger or equal to 0. Right? So we immediately have this conclusion: alpha always larger or equal to beta square, or the beta square always smaller or equal to alpha. So beta has its up limit. You cannot go over. For given alpha, for given alpha, the beta and large beta value cannot go over alpha. That is this first conclusion. So now we know the beta has a limit, not arbitrary. The limit for given alpha is limited within the certain number. Okay. So now I define the max value. Okay. Use the upper limit. If there, so that now if we define this, then you can see J plus here. We know J plus, the row played by J plus, that will change this one by increase one limit, right? So if then J plus apply the beta maximum has to be equal to 0, because you cannot increase beta to beta maximum plus 1, since no such states, right? That is, we are going to use this property. So that is, that be equal to 0. Then now, let's use this one. J minus. Let's example, right? Let's example. examine the G minus G plus. Let's look at this term. Because we know G plus applied this case with 0, so now we are going to see what this is equal to. Okay. Because we know G minus G plus, and then it's this one, right? This one. Equal to G square, that's equation 5, minus G Z square, minus H bar G Z, right? So, okay, the left-hand side of this one is G minus G plus alpha beta maximum. That's equal to 0, since this term is 0. Then we look at the right-hand side. So G minus G plus alpha beta maximum, that is equal to, equal to here, G square minus GZ square minus H bar GZ. Alpha beta maximum. We have this. Okay, so we know this is all the eigenstates of G square and GZ. So we can immediately get this H bar square alpha minus H bar square beta maximum square, right? This square, and minus H bar square beta maximum. Alpha beta maximum. Right? Then the left-hand side is 0. So if this is 0, that means alpha minus beta square maximum minus beta maximum is equal to 0, right? Because that's equal to 0, and that means this case cannot be 0, right? So only this one equal to 0. Then from this 0, you will have, that means you have the relation, this alpha equal to, we move to the left-hand side, right-hand side of beta maximum, plus 1. So that means, yes, we do have a maximum beta maximum, and the relation between beta maximum and alpha is exact. For getting alpha, the maximum value of beta is for this. That is, we apply the G plus, right? Now we are going to find the G minimum. Okay, so now because G minus apply this alpha G maximum, it will always give us this, you go to states, alpha will not change, and G maximum will minus 1, right? Then you keep continuing G minus to the nth times, apply this one, is to go to G minimum, beta minimum, right? We just plate, because we know it's from, each term is reduced by 1 unit. Then let's start from the maximum value of beta, try to reduce until here, see the lower minimum value we are going to define, that is the limit of the minimum value of beta. Therefore, we are going to apply G minus to minimum to be 0, right? You cannot go lower. So we are going to, same thing like here. We use G plus, apply the beta max equal to 0, but G minus go to the G minimum is also go to 0, and we can also do the same thing. So here also exam G plus G minus applied alpha beta minimum. This is G minus G plus, and that's equal to the same, right? So if I use this G, I just erase, but you can remember the G square minus GZ square, but plus, right? G minus multiplied G plus is this minus H bar GZ. and J plus multiply J minus, here is plus, remember this? So here is plus. That equals this. Then the left hand side, again, left hand side is equal to 0, since J minus cannot lower this beta minimum, this state. And the right hand side, again, since the eigenstates of J square and Jz, so we have plus b, h bar square, h bar square alpha, first term, minus beta square, minus h bar square, beta minimum square, and plus h bar beta minimum. Space here. Alpha beta minimum. Right? Then from this, because left hand side equal to 0, then we have another relation for beta minimum. So we have alpha equal to, let me just write down against alpha minus beta minimum square plus beta minimum equal to 0. So alpha equal to beta minimum minus 1, right? Okay, now we have almost reached to what we expect. We combine this together and use just very easily to mathematically solve. So alpha equal to both, right? So we have a beta maximum plus 1 equal to beta minimum minus 1. So this is very simple, you just multiply with beta max square, and so you have beta maximum square minus beta minimum square and plus beta maximum plus beta minimum, right? Equal to 0. And here beta maximum minus beta minimum and beta maximum plus beta minimum minus plus 1 equal to 0. Wait a moment. Yeah, plus this plus this plus this is plus. Plus, right? So we have two solutions. Beta maximum equal to negative beta minimum. Another is beta maximum equal to beta minimum minus 1. Which one is allowed? This one is not allowed, right? Because maximum must be the minimum. You cannot lower the minimum value. Minus 1 is much lower than this, and this not exist, right? That makes sense? So this one is not. This one is allowed. And that is the relation between maximum and minimum. Because maximum, beta maximum cannot be lower than beta minimum. So that is the this one. Then now we are going to go back to this one. So we are going to see what is the value. We just know the relation between this one, right? But what is the allowed value for beta? That's because J minus multiply n times on the alpha beta maximum, I think yes, beta maximum is finally reach to alpha beta maximum minus n should be equal to alpha. That means the minimum. So let's try to reduce by J minus to reduce the state by 1 unit and play n times. Then we press n times, must be go to the terminate to this one, right? So this states is this states. So we have the relation beta maximum minus n is equal to beta minimum. Then beta maximum equal to beta minimum plus n, right? Okay, and the beta minimum is negative beta maximum here. So move the beta maximum outside, the right hand side the beta maximum is equal to half n. That gives us value. So n here, n is the integer, right? Because we place n time. Then this one means the eigenvalue of Jz either integer number or half, right? So that is the discuss here. Okay. So that means that this value, beta value, is either integers or half non-integer. Only two choice, no any other choice. That is in the nature you will find we have only two types of the spin, right? The elemental particle, we put here, we didn't have any addition condition, right? We just apply the general property of the operator, angular momentum operator, then we prove that this only have these two categories. That is up to here. So now we are going to use visualization alpha, right? So okay, now we summarize. So alpha equal to beta maximum plus 1, and beta maximum equal to half n. So combine these together, we are going to introduce J. Now we are going to use the quantum number J here, and beta is n. Okay, sorry. So we have introduced J. J is equal to beta maximum minus half n. And we are going to introduce m is beta. So in this case, if we introduce, then the alpha equal to, we just beta is j minus half n, right? And let's see. This just frustrating this one, right? This beta is n, right? So that is, you see here, you substitute this beta equal to j half n, right? So that is j half n. N is integer numbers. Then here, let's make that one. Oh, okay, sorry. J actually is, J is not, I don't think, J is just beta max. Okay. So now, instead of using alpha beta, we are going to use J and M as a quantum number. J can stay either 0, half, 1, 3 half, 2, and all this allowed number. And the M, what is allowed M? Because here we have this, so M is always right? That is with this. And J, since that means M, because J maximum, beta maximum is J, and beta minimum is equal to negative beta maximum. So that is negative J. So this is the allowed value for J, for M, and the allowed value for J. Now we obtain the quantum number for alpha and beta. That is for the eigenvalue of this J squared and J. Okay. And here, so how many allowed for giving J? How many? 2J plus 1, right? We have a 2J plus 1 of M value when the J is given. All right, I think that is, we discussed general formalism of the angular momentum operator. Then next Monday, we are going to play with some of expectation value and detail, then we go to the spin operator.
It's just funny to me. It's like halfway through their work, they just decided they didn't like beta anymore. So they're like, what if beta was M instead?
Yeah, beta usually is a real number, maybe 1.02. So usually people think, why not use the integer number or half integer? It's all people.
Okay.
Yeah, that is just replace. Since sometimes beta is some of with some decimal place or alpha. So usually it's just some number.
Where your M's and N's.
Yeah, so this is a quantum number. Usually we use quantum number as G, M, L, N, those. So just replace.
Yeah, but we know better now, you know?
Yeah.
We don't need to carry on, like, that was a mistake historically, we don't need to carry it on, right? Like,
Talk to the electron.
I mean, you get what I'm saying? That's just,
Yeah, go ahead. Yeah.
no, it was a stupid joke, and now it's all, now my cringe is forever on recording.
Thank you, Jacob.
Yes.
What?
Are you going to keep those records?
I don't know.
It's good at church.
When he's like 54, he's just gonna
Yes,
like open it up and be
open
like,
and override.
Dr. Yu, lecture 6.
Sorry.
This is my favorite lecture.
This is a kind of way.
Today.
Yeah, I think this way may help you to analyze the other unknown operator properties and how to analyze the eigenvalue. That is, the plus minus really help.